I want to show you an example that makes use of the switch case statement, and it's really interesting example of the use of fractals. So, in general, with the switch case statement, you starts with switch, ends with end, and then you have a switch expression, which is either a scalar or a string. And then, depending on what the value of that switch expression is, you can have certain statements execute. So if the switch expression has value 1, then it will execute these statements. If it has value 2, it'll execute these statements. And then if you want, you can put in an optional otherwise, that if the switch expression doesn't have any of these values, then this group of statements will be executed. You don't have to do that. You can set it up so that it only executes upon certain values, but if you want something that'll execute no matter what, you can do that as well. Now, this particular example is a type of fractal known as a iterated function system, and this one in particular is known as the Barnsley fern. It's described in a book by a British mathematician by the name of Barnsley. It produces a very interesting result that you wouldn't expect upon just one glance at the algorithm. So the algorithm is an iterative computation where you start with a certain data point and then you compute the next coordinate based on an algorithm, and the algorithm is dependent on a probability. So 1% of the time, this is the algorithm that will be executed. The next x is simply equal to 0. The next y is simply equal to 0.16 times the previous y. Now 7% of the time you're going to execute this algorithm. And again, the next x coordinate is given by 0.2 times the previous x coordinate minus 0.26 times the previous y coordinate. And then similarly for the new y, it's a function of the previous x and y, and then also an offset. Another 7% of the time you're going to execute this algorithm, and then all the rest, which is 85% of the time, you will execute this statement. So then the question is, well, how does this actually work? And the guts of the function is listed in here, but let's go ahead and switch over to MATLAB, and I'll show you the entire program. I want to credit my colleague, Professor Doug Lawrence, who has used this in other course offerings that were related to MATLAB at Ohio University. So we start off, clear all the memory, close all the figure windows. We're going to execute the hold on command, which means that you're holding the figure, and that's because you want every data point that we compute to show up on the screen. We're going to need a whole bunch of points. 100,000 takes a while to run, but if you do much less than 10,000, it doesn't really look good. Start off, just initialize first coordinates to be 0, 0. I've got a weight bar here so that as it executes, you can see the weight bar scrolling along. And then we go into the main loop. So we're looping over all those points. We decided we were going to do 100,000 points. First thing we do is pick a random number. And the MATLAB RAND command chooses a random number from a uniformly distributed random variable that over the interval of 0, 1. So you pick a random number, and then, depending on what that random number is, you specify what's going to end up being our switch expression. So if p is less than 0.01, then we know we're in that 1% range, so we'll set equals to EQ to 1. If it's less than 0.08, which means that's a 7% percent distance from 0.01 to 0.08. So if it's not less than 0.1, but it is less than 0.08, then set equal to 2. Otherwise, if it's less than 0.15, set equal to 3. And if none of that is true, then we're in the other 85% of the case, and so then we set equal to 4. All right, so based on the random number that we've chosen, we've specified our switch expression. And now we can use the switch case in order to execute the iteration algorithm with the correct update. So if we're in the 1% case, for case 1, then the new x is equal to 0, the new y is equal to 0.16 times the previous y. If we're in one of the 7% cases, we do this. If we're in the other 7% case, we do this. And finally, if we're in the 85% case, then we go ahead and run this algorithm. When we're all done, then we have executed one of the 4 algorithms. We then plot the new coordinate. Again, we executed, that's up above, we executed the hold on command so that the new data point would plot on top of the previous ones. And then we set x0 and y0 equal to the new x and y, and update the weight bar if necessary, then go back up to the top for the next data point and do it all over again. And when we're done, then we can release the holds so that subsequent plots are done on new figures. All right, well, this thing takes a little while to run, so I'm not going to waste screen time to do it right now. But if you go ahead and run this thing, what you will find when it's done is you end up with this plot. It's really quite amazing to think that that simple algorithm that we just coded up yields this just unarguably beautiful picture of a fern, which is just based entirely on this fractal mathematics. Anyway, so this was an example of the use of the switch case statement. You will get a chance to put this into practice with regard to a half-wave diode rectifier example that I'll introduce briefly in a separate screencast.